an interesting effect. We're getting the picture that these charged particles have a hard time crossing magnetic field lines, right? That's when the force is the strongest. When the particles try to cross a magnetic field line perpendicular, you get a maximum force. And what direction is it? It's perpendicular to the velocity. But if they try to travel along a magnetic field line, there's no force, right? They can travel along magnetic field lines very well, but they have a real hard time crossing perpendicular to a magnetic field line. So an example would be the Earth. The Earth has these magnetic field lines that encircle it. And the sun over here gives off charged particles. Sometimes more than at other times when there's a lot of solar activity, solar flares, things like that. We get this flow of charged particles toward the Earth. And what happened? Those charged particles, they have a hard time crossing perpendicular to magnetic field lines. So when they get to the magnetic field line, they feel a force, and they want to, what do? They want to wrap around those magnetic field lines. But if they have some component of their velocity that's parallel to the magnetic field line, if they're coming in at a slight angle, then what happens is they end up doing that, right? They end up spiraling around the magnetic field lines. And if they had some component of their velocity in the other, slightly in the other direction, they end up spiraling around the field lines in this direction. So you can see that charged particles, because they have a really hard time crossing, if they try to cross this field line, they feel a force perpendicular that makes them want to circle it. But if they have a little bit of a velocity in this direction, as they come in, they circle it, but they keep moving along the field line. They want to go along those field lines. And what do we get? We get the northern lights and the southern lights, the aurora, up here and down here, right? Where these charged particles are hitting the atmosphere of the Earth and exciting the gas molecules that make up the Earth's atmosphere. And then when those gas molecules go back to their ground state, they give off light in a certain energy. So it depends what's in the gas here, right? But you get to see greens from nitrogen and certain colors. The pinks and things that you see are from argon and some other gases that are in small quantities in the Earth's atmosphere. Has anybody seen the aurora? Nobody's seen it in person? No. I'm the only one? It's quite interesting. Sometimes it just looks, you go outside and you think, wow, the clouds are lit up in this greenish color. That's odd. And then you realize that there are no clouds. It's a clear night. And it's just kind of this glowing color, and maybe it moves very slowly and like clouds kind of blowing in a slow wind. And then other times you get more vivid colors, the pinks and things, and then it flows. It actually looks like it's flowing in the sky. It's very interesting. I recommend putting that on your list of things to see. So charged particles moving along the magnetic field lines, hitting the Earth's atmosphere, exciting those gas molecules, and when they drop back down to their ground state, they give off energy in the form of light. All right. Okay, so far we have been talking about charged particles in magnetic fields, how they are influenced by magnetic fields. So what's the next logical thing to talk about? A whole bunch of charged particles moving together. Right? What's that? That's a wire carrying a current. So you might think now, if a single charged particle moving in a magnetic field feels a force, then a current carrying wire would also feel a force. And what we end up with is this equation. The force on a current carrying wire is the current times the length of wire that's in the magnetic field times the magnetic field times the sine of the angle between them. And of course, the units on force are Newton. So if you use amps, meters, Tesla, then you get newtons for force. And we can look at some examples like we did to start class. We can say, what's this one going to be? We have a magnetic field in this direction, and we have a current carrying wire. And let me do it this way. Let's pretend for a minute that we could confine the magnetic field to within this region. And we have a current carrying wire. And this will be distance L. Okay, force. What's the magnitude? What's the direction of our force? Zero, because they're in it's parallel. The movement of the charges is in the same direction as the magnetic field lines. There's no force. And what is the current? The current, we pretend that the current is positive charges moving in that direction, right? So what's the direction of the force? Well, we'll get there in a second. Let's do this one. Because we pretend that the current is positive charges moving in that direction. So a positive charge moving this way, a magnetic field that way, would give you a force into the page. Okay? Let's see. Let's do... and they're 90 degrees apart, so force is equal to ILB. Okay?